Hello, physical science students. Welcome to our unit on sound. We're going to start this video with this video of the nature of sound, and we are going to look at a few different things. We're going to look at sound waves and what affects the speed of sound and how our ears allow us to hear. So let's take a look at sound waves. All sounds are made by vibrating objects. You'll remember that air itself is composed of matter, and so when an object like a speaker here vibrates, it collides with some of the particles that are in the air. It transfers that energy to those particles, and those particles collide with other particles, passing the energy further and further along, and that energy originally transferred by the vibrating object continues to travel through the air in that way. And the process of that energy transfer forms a sound wave. Remember that sound waves are longitudinal waves, also called compression waves. And remember that a longitudinal wave is composed of two different regions. One of the regions is a compression, and another of the regions is the rarefactions. If you'll think about a speaker itself, when the particles near the speaker are pushed together, they form a compression. And then when the speaker moves inward, the particles near the speaker are spread out and there is a rarefaction formed. As long as the speaker vibrates back and forth, we get sound waves being produced. So how fast does sound travel? Well, it really depends on whether sound is traveling through air, water, or matter. And you'll know if you've ever been underwater, you can hear sound underwater. Also, if you put your ear on your desk, and you can hear sounds that are traveling through that desk if someone's tapping on the desk or scratching or banging on it. So how fast are these sounds? Well, it really depends on some other factors, but overall, sound actually travels the slowest in air. It travels faster in water, and it travels even faster in solid matter. I should say solid matter because these are all matter. But in a solid, sound actually travels the fastest. It depends, however, on what type of solid it is. The different solids will carry the sound waves faster than others. What about outer space? How fast does sound travel in outer space? Well, in outer space, there is no atmosphere, and there are no particles in that atmosphere to transmit the sound waves. Therefore, sound waves cannot travel through the vacuum of outer space. And that's why astronauts carry radios to be able to communicate to each other, because sound waves do not travel in outer space. So the speed of sound depends on our medium, if it's a solid, a liquid, or a gas. And right down here we have gases. Sound waves travel the slowest through gases and the fastest through solids. But there are other factors that affect the speed of sound. The temperature of the medium affects it, the density of the medium, and the elasticity of the medium. So let's take a look at temperature first. As the temperature of the medium increases, and this in particular affects gases and liquids as well, but gases would be the most affected by this temperature change. If we increase the temperature, then that means the particles that make up that medium will move faster, makes them more likely to collide with each other, and if the particles collide more often, then more energy can be transferred in a shorter period of time, and as a result, the sound waves travel faster. So raising the temperature will increase the speed of sound. Let's look at the idea of density. Well, the density of the medium, the more dense the medium is, the closer together the particles are, and therefore the speed of sound will be faster in a more dense medium. And that's a lot of the reason why solids the speed of sound will go faster through a solid, because it is generally much more dense than a liquid and definitely more dense than a gas. Now let's take a look at elasticity of the medium. The word elasticity in science, it means the tendency of an object to rebound to its original state when it's been deformed. So a rubber ball is elastic because it tends to spring back to its original shape after you squeeze it. That would be elasticity. Elastic objects also rebound more quickly when sound waves travel through them. So sound waves will travel more quickly through elastic objects. Solids tend to be more elastic than liquids, and liquids tend to be more elastic than gases. So the more elastic the medium is, the faster the sound waves will travel through them. So let's look at one last question, and that is, how do we hear? Let's take a look at our ears. Our ears and our brain work together to interpret sound waves. And our ear is made up of 3 parts. We have the outer ear, the middle ear, and the inner ear. The outer ear includes the visible part and then this passageway here called the ear canal. This outer part right here gathers the sound waves. And the shape of the ear is such that it helps to capture and direct those sound waves right into this ear canal, this passageway. And that ear canal leads to the eardrum. The eardrum right here is a tough membrane. It's about 1/10 of a millimeter thick, and it transmits the sound from the outer ear to the middle ear. So when the eardrum here vibrates from the sound waves, it passes those sound waves onto 3 tiny bones in the middle ear. And these bones are called the hammer and the anvil and the stirrup. They make a lever system that increases force and pressure exerted by the sound waves, and they amplify those sound waves. This stirrup here is connected to a membrane called an oval window, and that is right here. That vibrates as the stirrup vibrates. When the membrane in the oval window right here vibrates, the sound vibrations are transmitted to the inner ear. And the inner ear contains this structure called the cochlea. It's a spiral shape, and it's filled with liquid and tiny, tiny hair cells. Those hair cells inside of the cochlea vibrate, and nerve impulses, because of those vibrations, nerve impulses are sent to the brain via the auditory nerve. That is how the sound waves are converted to nerve impulses. Here is a picture of those tiny, tiny hair cells inside of the cochlea. This is magnified roughly 5,000 times. So these hair cells are extremely tiny, and most hearing loss is due to damage or destruction of these tiny hair cells. And when these hair cells are damaged or destroyed, it's permanent because the hair cells in the cochlea of humans and other mammals do not grow back when they are damaged or destroyed. So it's important that you protect your ears and not damage them with noises and sounds that are too loud and damaging to them. Are you looking for some advanced ideas? Do some research on hearing loss. What are other causes of it? What treatments are available? How can hearing loss be reduced or stopped? Also, what do the terms Mach 1 and Mach 2 mean? What do they have to do with the speed of sound? Do you have other questions? Please ask them. Do some research. Come in and show me what you know, and I look forward to seeing you in class.